Well, welcome to the session of universal hashing and authenticated encryption. I am Tetsu Iwata, and we have the session. First talk about map speeding up bytes mapped by around 20%. The work by Bishop, Brown, Mark Manning, Samuel Meres, and the talk will be given by Mark.
Okay, thanks, Tetsu, for the introduction. So this work is about MAC function. So what's a MAC function? A MAC function is a function that gets as input a secret key, and that takes an arbitrary message and turns it into a digit of fixed length, say 64, 128 bits. The message can, of course, be arbitrary length. What's the goal of a MAC function? A MAC function typically signs or authenticates a message. And a verification function takes also the key, and then it gets as input the message and the tag, and it outputs typically this bot function, this top value if the tag is correct, and the bot value if the tag is incorrect. What security do we typically want? The main goal we have is usually enforceability. So it should be hard for an outsider that can get many of these message tag combination tuples to find a new tuple that succeeds. If this MAC function satisfies this property, we say that it's enforceable. Sometimes we go for a stronger property, which is PRF security. And PRF security means that this MAC function for a secret key should be random. Stated differently, that the PRF security of the MAC function should be small. I will not discuss PRF security, that kind of stuff. Basically, what we aim for is a MAC function that behaves random. If you think about MAC functions, the hash function, the MAC function, the message is typically of arbitrary length. And a very efficient way of making a MAC function is to use a kind of a weaker function, typically a universal hash function, to process the bulk of the data. So the message can be of arbitrary length. You use a universal hash function to process it to something smaller or fixed length. And then you can finalize it with a stronger cryptographic primitive. That's a very popular way of making a MAC function. It's called the hashed and PRF design or protected hash design. And you see it a lot. And it's proven secure. This construction is proven secure if the hash function is epsilon universal. I will get back to the definition of this later. And F is a pseudo-random function. And you can even make it more general. You can replace this pseudo-random function by a block cipher or the truncation of a block cipher as some security loss. You can actually add an extra message block here of n bits, as long as the hash function is extra universal. But the bottom line is the efficient way of making a MAC function is to use a universal hash function to process the big bulk and a stronger cryptographic primitive to protect it. And if you think about this, ideally, the hash function is parallelizable. This could potentially speed up the implementation a lot. And if you now look at the very well-known MAC functions following this design, there are a couple of them. So a very famous one is protected counter sum by Bernstein from 1999. The idea is that you take a pseudo-random function that gets as input a counter and a message block. You process it, you do a checksum, you add all the values, and then you protect it. So this is a protection. This serves as a universal hash function. It's parallelizable. It can be made very efficient. Another famous one is PMAC. And PMAC, this is a slightly different picture because the masking is a bit different from the real PMAC. But the idea is that you compute a subkey from the big key K. So you encrypt a 0 string to get a subkey. And then the message blocks are processed block by block, masked with 2 to the power 1 times this subkey, 2 to the power 2 times the subkey, etc. So you mask the inputs, and then you process them with the block cipher, you do a checksum, and you protect. Again, #10 PRF or #10 PRP. Another interesting one is the LightMac. LightMac is also inspired by protected counter sum. Instead of putting the counter separately here, because here you need a compressing PRF, you take a block cipher, you concatenate the counter with the message block. Counter 1 with first message block, 2 with second message block, etc. And then you protect at the end. So far, so good, famous schemes, but if you look at these ones, the part that serves as universal hash function, also in the security proof, it is typically proven that this portion behaves like a universal hash function, is in practice almost always built from a block cipher. So that sounds overkill. So you use a strong primitive to build a universal hash function, which is typically required to have weaker properties. And intuitively, it should be possible to build the main bulk processing function from universal hashes. So ideally, we don't want to use a block cipher here, but something that's lighter, like a universal hash function. And this is the goal of this work. So what we try to do is we try to develop a parallelizable domain extender for a universal hash function. So if you take like a small fixed length universal hash function, you can magically turn it into a parallelizable variable input length universal hash function. The contributions in the paper are fourfold. So first we introduce EliHash. So EliHash is a parallelizable domain extender, a universal hash function of arbitrary input length built from universal hash functions of fixed input length. EliMac, which is a MAC function on top of EliHash. So that's basically the hashed and PRP design using EliHash. Eli stands for extremely light MAC because it's based on light MAC. We instantiate, so we give a suggested instantiation using round-reduced AES. And also in the paper, we describe an attack on Marvin. And Marvin, that's an interesting one because there was an earlier attempt to use a fixed length universal hash function and turn it into a variable length one. But we found out that this didn't work. The proof didn't hold. You can find flaws in the reasoning. The core idea basically there is that if you take 4 rounds AES and you add a lot of them, it turns out that this is not secure. I will not discuss this, the flaws in the work of Marvin. I will only discuss EliHash, EliMac, and the instantiation. So starting with EliHash, let's consider we have 2 universal hash functions of fixed input length, fixed output length. So we take H, which operates on a key space K prime, and it gets as input some counter between 1 and mu. And mu is the maximum block size. So typically you take 32-bit counters in LightMac. Here we take a mu can be at most 2 to the 32. So you have the master key space key prime, a counter, and it gives you another key from the key space K. And then we take a universal hash function I that takes a key from this key, and then an input block goes to an output block. And EliHash is simply designed as follows. So you take the master key, you have the counter going into H. This gives you a subkey to I. And then the first data block gets processed, second data block gets processed, etc. So instead of just adding universal hash functions, we have to do a trick to build it from 2 universal hash functions. So it looks rather simple, and it is actually analyzable, but it is not as easy to prove as it looks like, because what we typically want is, of course, we want that EliHash behaves like an XOR universal hash function. Because if we later instantiate it to a MAC function, you need that the big bulk is processed with an XOR universal hash function. What this means is that we want XOR universality of EliHash, basically that if you take any 2 different inputs, x and x prime, in this case, those are vectors of length at most mu. So if you have 2 strings, x and x prime, and if you take any value y, the probability that EliHash of x plus EliHash of x prime equals y should be small. If this is the case, then EliHash is an XOR universal hash function. Ideally, we would like to rely on the XOR universality of H and I. However, in our case, that doesn't work. The main reason is that we add typically more than 2 output values of I. And that gives problems if you add XOR universality, because in the equation of XOR universality, you add 2 of them, and you cannot generalize this. You cannot use this definition for adding more than 2 values. So instead, we need a stronger property, not on I, but on H. So in H, we require a stronger property, which is mu independence, which roughly means that if you take any distinct xi and yi, mu of them, so mu xi's and mu yi's, the probability that if you take a key, and that in this case, H of xi goes to yi for all values, is at most delta to the power mu. So this is the delta independence of the universal hash function. It's a stronger property. And we use this one for H. It sounds like a strong property, but the fact that we use a small counter space of 1 to mu kind of helps, and it makes sure that the instantiation later on works. So what's the general result? So we say like if mu is the maximum message length, the maximum number of blocks that get processed, if h is delta mu independent, so if h, the one that processes the master key and the counter values and generates the subkeys, satisfies delta independence, and if I is XOR universal, epsilon XOR universal, then Eli hash is XOR universal up to this term. It's a bigger term, so you get some loss, which makes sense because you have a variable length hash function. But typically, you would like to use a hash function h, for which is delta universal for delta close to the key space, or for which mu is small. But we're looking at lightweight applications, so mu is typically small. Anyway, I would like to show a little bit the proof idea, just a very high-level idea. We want to prove XOR universality of Eli hash, so we say consider any two different strings, so x and x prime of potentially different length, and any output value y. Our goal is to upper bound the probability that if you take a random key, that Eli hash of x plus Eli hash of x prime equals y. That's our goal. The first step is to simply count the number of tuples, number of keys into I for which this equation holds. Because the x values are given, y is given, we can just sum over all possible key inputs to all values I, which are key tuples, for which this collision, this XOR collision works. So just we count all these key tuples. Then the probability that the hash function h hits one of these key tuples is at most delta to the power mu because of this delta independence. You have the inputs, you have the outputs, delta to the power mu. Then we still have to bound the number of possible key tuples. And with a bit of work, we find that this is at most the key space to the power mu times epsilon. And then you combine everything and you get our bound. You just multiply these two terms. Then for Eli-Mac is nothing else than just taking this universal hash function and protecting it with a truncated block cipher. So you take two not necessarily distinct universal hash functions, h and I, you take a block cipher E, and then Eli-Mac is just basically light Mac, but with the hashing part replaced by Eli hash. So the security proof, I will not discuss the security proof, but it simply takes Eli hash as universal hash function, and then you compose universal hash with a protection, in this case truncated permutation, and we just combine some proof techniques. So this is not a very spectacular proof. I will not discuss it, but you can believe me, we prove this. And it is kind of, well, it is secure. It's actually tied. So we also give an attack attacks that match the security bound. So the main goal was actually to compare it also with LightMac. And LightMac is an ISO standard, LightMac AES. So they use 10 rounds of AES for all the building blocks. So we thought like the main goal, the main incentive originally was to use for the hashing round reduced versions of AES to speed it up while still getting some provable security guarantees. So it now makes sense to actually instantiate this scheme. So instantiate H, I, and E using AES. And in this case, AES 128. So we take AES 128 as building block or round reduced versions of AES 128 as building block, and we instantiate this scheme. For E, the block cipher that protects, it needs to be cryptographically strong, so we just take 10 rounds of AES. For I, we take 4 rounds of AES. There has been analysis that shows that 4 rounds of AES has good differential properties. Of course, this is with some assumptions. So if you assume independent round keys, you can derive bounds. We simplify this, so we actually don't put the key input here, but we take key plus X. So I gets a key input and an input block, M, which serves as X, and you just, I is defined as 4 rounds of AES with a 0 into the key schedule and K plus X, so the two inputs added bitwise into the data path. Instantiation of H is a bit more subtle because we need independence. We need mu independence. And for this, XOR universality does not work. XOR universality does not imply mu independence. Mu independence is a stronger property. But still, based on the best cryptanalysis results, it appears that 7 rounds would definitely suffice. So note that we take a 32-bit counter, which can just glue it together 4 times. It gives 128 bits. And this means that mu is at most 2 to the 32. And the best attacks on 7 rounds need, say, 2 to the 97-ish chosen plain text. So you can never get there in this application. So based on the cryptanalysis results, it appears the 7 rounds could suffice for H. So now the quick question, the interesting question is, if you compare this instantiation with LightMac, how would it look like? So let's take a LightMac. Let's take a counter that goes to 32 bits. So mu is at most 2 to the 32. This means that in LightMac, you encode the counter also using 32 bits. LightMac uses a full AES block, full AES construction per block. So if you have AES on, if you have LightMac on L blocks, you make 10 L AES rounds. You evaluate AES rounds, you evaluate L AESs, so 10 times L AES rounds, which is in total, well, 0 pre-computation, 10 L. So you sum those, you get 10 L. So the total number of AES rounds in LightMac would be 10 L. In EliMac, you would have 7 times L minus 1, because you have one block that's dealt with separately. As pre-computation, possibly 4 times L minus 1 for the online, and then 10 for the protection. So that's 11 L minus 1 AES rounds. So that's the comparison between LightMac and EliMac. The downside is this looks like EliMac is more expensive than LightMac. But as a matter of fact, the difference between LightMac and EliMac is that the block size is different. Because on LightMac, you have the counter and you concatenate it with a 96-bit block. And here we can take a 128-bit block. So that gives you an improvement if you do the math of around 20%. Of course, and the cool thing is you can do the pre-computation that really speeds up significantly, but on the downside, you have to do extra storage because you have to store the keys. I would like to make some important notes. Of course, the assumptions are different. So in LightMac, you assume that AES is PRP secure. We need PRP security of AES, but we also need that 4 rounds of AES is XOR universal, 7 rounds is mu independent. And the security bound is slightly worse. So based on the assumptions for AES, for LightMac AES, you get 64 bits of security. We get 56 bits of security for the instantiation. So there is this trade-off possible. So what we also did, we benchmarked this. So we actually did the implementation, efficient implementations of EliMac AES. So the instantiation I gave on the previous slide, we compared with the LightMac AES, PMAC2 AES, and ZMAC Deoxys DBC256. Not just counting, but actual implementations. They are all parallelizable, all with length independent bounds up to some degree. So up to some length, up to some restrictions, like the generic version, that kind of stuff. But it's fair to kind of compare these variants. And we compute the CPB for different message blocks. And you kind of see this 20% gain. So EliMac speeds up, LightMac speeds up all the other ones too. P.C, I don't, stands for the pre-computed keys. So you see that if you take EliMac with pre-computed keys, it significantly speeds up. But of course, you have extra memory storage requirements because you have to store all the subkeys. And again, I would like to mention the assumptions differ. So if you compare the assumption for LightMac or assumption for EliMac, we have different assumptions on AES, but at the same time, ZMac makes an assumption on the tweakable block size. So you have different assumptions. So it's a bit comparing apples and oranges. So to conclude, so what we introduced is EliMac and EliHash and EliMac. So it's a domain extender for a universal hash function. If you take a fixed length universal hash function, develop a variable length universal hash function. And it turns out to be more subtle than one thinks. Just adding the universal hashes is problematic. So what we required is we needed to kind of make a trick on the construction, and we required 2 different assumptions on the underlying primitives. Of course, you can get a significant speed up in the instantiation. What I think is an interesting question is, can you really do this with XOR universal hash functions alone? Like a domain extender just using universal hash functions, and it seems hard to do, but at least avoiding this mu independence, which is a strong requirement, would be an interesting question. So that concludes my talk. So I would like to thank you for your attention.
Thank you very much. So we have time for questions. Yes, Kate.
I have a question about your performance results.
Yes.
When you compare to PMAC, intuitively, I would expect PMAC to be faster because you have the same block size and only 10 rounds instead of 11. But your results show that LEMAC is faster than PMAC on most cases. Can you comment on that?
Yes, so this is not the real PMAC, it's PMAC 2, which is a different variant. I forgot which one this is. And I cannot comment, well, I have to admit, I did not do the implementation. I cannot give the exact answer to this, but I think that's the source where it differs. And if you look at the normal PMAC, it's not length independent. So the security of PMAC, the normal one, is, as far as I know, not length independent. So that's why it was not taken into consideration, as far as I remember.
Okay, thank you.
Any other questions? Robin?
Okay. So what do you mean by the purely theoretical universal hash? I mean, the one of your open problem. Purely theoretical. What does
purely parallelizable? Yes, I mean basically, I mean this is kind of parallelizable, but you still do this trick, right? If you really, I mean, is there something that you can just add fixed length universal hashes without needing two universal hash functions here that are kind of, I mean, technically this is not parallelizable, this part.
Okay, thank you.
So like basically getting rid of the trick we had to apply.
Okay, one.
Okay. So this construction needs two assumptions about AES. So I mean that first is a 4-round AES about differential uniformity. But yeah, I know it is proven, but the round keys are independent.
Yes.
And you only use the single key for the input of the I, right?
So yes. So yes, it's true. So first of all, it's not true that you say we need two assumptions. We need three. Namely, this one needs to be XOR universal. This one needs to be independent. This one needs to be PRP. But you're right.
Yeah.
And this analysis was indeed, if you take like 4 independent round keys, we have 0 every time. So, well, 0 every time, no, but we don't put the key into the key. For that, we just assume that the same bound applies.
All right. Yeah. So the minor comment is that if we H outputs the 4, exactly 3 round keys independently, then you can remove the second assumption. Yeah, because as it it's
so if this one generates the round keys of this one.
Yeah.
Okay, that could be. That's an interesting option. We didn't think of this. Just why we don't put K comma X here is because then you have to do the key schedule stuff.
Sure.
But I didn't think of this one. That could be an option. Yes.
Thank you.
Okay, thank you very much. So let's thank the speaker again. So we move to the next talk. So the next talk is multi-mixer 128, universal key hashing based on integer multiplication. This is done by Ghosh, Palisa, Amiri, Eliasi, and Yuan Diamond, and Ghosh Tab will give a talk.
please. Thank you. Thank you for the introduction. Thank you for the introduction. And we begin with keyed hash functions. Keyed hash functions are a class of cryptographic primitives that can compress variable length inputs to a fixed size state under a secret key. And they can be used to build message authentication codes, code functions, or doubly extendable cryptographic keyed functions, or DEC functions for short, which is a generalization of max functions and stream ciphers. Now, the security of a keyed hash function fk is determined by its universality. And there are two notions of universality. First is the epsilon universality, which upper bounds the probability of obtaining a collision over two different messages. And there is a stronger notion of universality, namely the epsilon delta universality, which upper bounds the probability that two distinct messages lead to a specific output difference. Now, in this work, our goal is to design epsilon delta universal keyed hash functions, where epsilon is close to 2 to the minus 128. And we want to design the hash function for software platforms, by which we mean platforms which do not have AES or other cryptographic hardware instructions. And these platforms typically have single instruction, multiple data vector instructions. And these are the platforms that we target. To design such a keyed hash function, we follow the we use the parallel construction, which parallelizes a public function. This is a generalization of the parallelization of public permutations by Fuchs et al. And the construction works as follows. From a public function, which is a function f from a group G to another group G prime, we can build a keyed hash function that we call parallel f. And in this keyed hash function, we have the key space is G to the kappa, where kappa is assumed to be a large positive integer. So we make assumption of long independent keys, which can be pre-computed. The message space are all vectors with elements from the group G and whose length is at most kappa. And finally, the digest space is the same as the codomain of the public function f. Now, in this construction, we first have a message of any arbitrary length and a key k of length kappa. We first add the message to the key, and the addition is very simple. We add them component-wise up to the length of the message. And finally, fk of m is the same as f of m plus k. And how does f operate will be shown in the next slide, which is this. So we have a message m. We have a message m and a key k, and we add them block by block. So m0 is added to k0, m1 is added to k1, and so on. And after adding the message with the key, they are processed by the public function f. And finally, all the outputs are summed together to form the digest. Here, one thing to note is the addition between the message and key happens in the group G, and the additions of the outputs of f happen in the group G prime. So they are not necessarily the same additions. Finally, we look at the universality of this construction. The universality of this construction in case when f is a permutation was studied by Fuchs et al. In case of public when f is a public function, instead, the universality results are as follows. So the universality of this construction is determined solely by the fixed length public function f. Namely, we need two notions. The first is that of the differential probability of a differential, which is just the fraction of the inputs in the input space that with the given difference A leads to an output difference delta. That's the differential probability of the differential A delta. And the other notion that we need is that of IP, which is the image probability. This is just that if you have an output Z, then the IP of Z is simply the number of pre-images of Z divided by the size of the divided by the number of possible inputs. Now, we denote the maximum possible value of DP and IP as MDP and MIP respectively, where for MDP, we take the maximum over all possible differentials with a non-zero input difference. And for MIP, we take the maximum over all possible outputs. It was proven by Ghosh et al. That this construction is epsilon delta universal with epsilon, the maximum between the MDP and MIP. And this bound is tight as long as the bound for the MDP and the MIP are tight. So this means that in this construction, the universality of parallel F is reduced to simply obtaining the maximum differential probability and maximum image probability of the underlying public function. Moreover, the universality thus obtained not only takes into account messages of equal length, but also messages of variable length. Next, we look at a very fast keyed hash function on software, which is the NH hash function, parameterized by two things, kappa, which is an even integer larger than 2, which is often referred to as the block size, and W, which is referred to as word size. This is typically 8, 16, or 32. Now, NH is very fast on software in our target platform because it makes use of vector instructions for integer multiplication. And actually, this NH hash function can be viewed as a function as the parallelization of a public function, and that public function is very simple. It's simply the integer multiplication of two W-bit integers. So we have two W-bit integers X and Y. We just compute their product, and there are no reductions involved. If this function is parallelized in the parallel construction framework, then we have the NH hash function. To be more precise, in this framework, we have a message M, which is which can be broken into blocks, M0, M1, and so on. And each of these blocks are a tuple of W-bit integers. So each MI can be written as M2I, M2I plus 1. And we can do the same for the key. And finally, how NH works is as follows. So in each block, you have a tuple of W-bit integers as message, and the same for key. Then we can add them component-wise, and the addition are always modulo 2 to the W, because we are operating over the group Z over 2 to the W Z square. Then we take the multiplication of these two components. So for the first block, the output would be M0 plus K0 times M1 plus K1, and so on. And all these results are finally added together to form the digest. The additions are denoted in different colors because the addition in blue is addition modulo 2 to the W, whereas the addition in red is addition modulo 2 to the 2W. The authors of NH studied the universality of this hash function, and they proved that NH hash function is 2 to the power minus W universal on equal length messages. This universality is not sufficient because for W is 32, for instance, this is only a 2 to the power minus 32 universal hash function. To increase the universality to 2 to the power minus W3, the author suggests that we can apply a NH hash function with independent keys on the same message. And if the results are concatenated together, then the resulting hash would give rise to a key hash function that is 2 to the power minus W3 universal. The problem is that this would require T times as much keys as the base version of NH. The authors use the tuplets construction to make sure that the universality bound holds, but they only require a very small amount of extra key material, which is simply 2W times T minus 1. To give an example and be more concrete, if we look at NHT with word size 32 and T4, then that gives rise to a 2 to the power minus 128 universal hash function. And this only requires 192 bits of extra key material. And this is the fastest option for keyed hashing on our target platforms because the dimensions of 4 are very well suited to the SIMD instruction sets. And this is the function that we will be comparing our proposed keyed hash function with. Now, the authors also define a mode on top of NH. By mode, we mean this is a combination of padding, concatenation, and length annotation. And they do this to handle messages of arbitrary length, because now NH can only handle messages of very particular lengths. And to ensure that the universality bound also holds for messages that are of variable length. They make sure that this happens by making sure that collision between messages can only happen if they have the same, the messages are of the same length. So messages of different length can never have collision. Now, as we mentioned, that NH hash function follows the parallel construction. So we can also analyze its security in the parallelized public function framework. In this framework, the problem of obtaining the universality of NH hash function reduces to simply obtaining the maximum image probability and maximum differential probability of the W-bit multiplication. We show that the maximum image probability of a W-bit multiplication is upper bound by 2 to the power minus W plus 1, and this is a very tight upper bound. And the maximum differential probability is simply 2 to the power of minus W. This means that based on this framework, we can actually prove that NHT is simply NHT with W32 and T4 would simply be 2 to the power minus W plus 1 times 4. So that's 2 to the power minus 124 delta universal. And this universality bound actually holds over all possible messages. So we don't, without defining any mode on top of it, NHT is 2 to the power minus 124 delta universal hash function. In our approach to find the MIP and MDP of the W-bit multiplication, we also find a way to tightly upper bound the maximum possible value of DP of a differential for an input difference AB, and the maximum is taken over all possible delta. And we also obtain a special value, which is the DP of AB comma 0. So the output difference is 0 and input difference is AB. This corresponds to obtaining a collision at the output of W-bit multiplication. One more thing to note is that the input difference is a tuple because W-bit multiplication takes a tuple as its input. Now, with these, due to these, since we have efficient expressions to compute these things, we could actually compute the value of these DPs for all input differences. And we find out that even though the DP value is indeed upper bound by 2 to the power minus W, but they only happen for very few input differences, namely these four, A0, 0A, AA, and A minus A. And for most other input differences, actually the differential probability is way lower, which we show in this histogram. So here for W is 16. So for 16-bit multiplication, we computed the maximum possible value of DP for every input difference, and maximum possible value of DP over all output difference for every input difference. And we also compute the value of the DP AB comma 0 for every possible input difference. In the x-axis, we have the differential weight, which is simply minus log 2 of the differential probability. And on y-axis, we have the total number of differences. So the total number of input differences that attain that particular weight. The red points basically demonstrate the graph for the DP AB delta, where the maximum is taken over delta, and the blue line corresponds to the DP of AB comma 0. Here we can see so here we have these 4 points that we already mentioned before. So these 4 points account for all the points here, but we can see that there are very few points here that have relatively low weight, which means high DP. But if we go to the right, then we can see that most of the input differences lie here, where the weight is 31. So the differential probability is way smaller than here. So this means that we found out that for most of the input differences, the DP value is actually much lower than the upper bound. So based on our findings, we see that W-bit multiplication is indeed an excellent choice due to the very nice propagation properties. And we present the public function F128 that is based on this W-bit multiplication. And our proposed keyed hash function multimixer 128 is simply the keyed hash function that is obtained by parallelizing the public function F128. F128 works as follows. So it takes as input 2 vectors of 32-bit integers, and it outputs an 8-component vector of 64-bit integers. And how it works, it has a very simple expression, which we explain in the figure here. So we have X and Y as input to the public function F128. We apply a circular matrix whose first row is 1, 1, 1, 0 to obtain another 4-component vector of 32-bit integers, which we denote as U. We do the same over Y, but the matrix here is the circular matrix whose first row is 0, 1, 1, 1. Finally, we compute the Hadamard product of the vectors X and Y. So we component-wise multiply X and Y. So we compute X0, Y0, X1, Y1, and so on. And we do the same for U and V. And finally, we concatenate these results. And this is the output of the public function F128. So now after this, in order to find the universality of multimixer 128, we need to find the maximum image probability and maximum differential probability of these functions. For MIP, we proved that for all non-zero outputs, the image probability of Z is much smaller than the image probability of the output 0. And the image probability of the output 0 is simply close to 2 to the power of minus 127, which is the MIP of the public function. For the MDP, we note that the MDP of F128 is determined by the number of minimum active multiplication. What we mean by that is, for any input difference to this public function, we have 8 possible multiplication. That input difference will propagate to each of these multiplications, and clearly only the multiplications that have a non-zero input difference play a role in determining the DP of that differential. So we refer to these multiplications with non-zero input difference as the active multiplication, and the minimum number of so the input difference that leads to minimum possible number of input active multiplication will determine the MDP. Now, this to determine the minimum number of active multiplication is determined by the matrices n alpha and n beta, and we can find out this number. So we have this concept of branch number that conceptualizes this, and the branch number of an n by n matrix over W-bit integers is simply the minimum of the weight of X, where X is an n-component vector with elements where each component is a W-bit integer, and by weight we mean the number of non-zero components in X plus the number of non-zero components in n times X, and of course we have to take the minimum over all non-zero X. Now, n alpha and n beta are both matrices that have branch number 4. When we've proved that when AB is such that 4 multiplications are active, then the DP of the differential is upper bound by 2 to the minus 128. In particular, we also show that if you choose the input difference of the form A0 or 0A, the DP is always 2 to the power minus 128 if you choose the output difference to be 0. So the value of this DP is tight. So this is not an upper bound, this is an equality. And finally, we also show that for all other possible input differences, that DP is smaller than 2 to the power of minus 160. This means that multimixer 128 is epsilon delta universal, where epsilon is the maximum of MDP and MIP of the public function F128, which is 2 to the power minus 127 from the MIP of F128. Finally, we have some benchmarking and implementation results. First, we compare the number of operations per 256-bit input. NHT requires 16 integer multiplication, 32 additions modulo 2 to the 32, and 16 additions modulo 2 to the 64. And multimixer 128, on the other hand, only requires 8 multiplications, 20 additions modulo 2 to the 32, and 8 additions modulo 2 to the 64. And here we also implemented multimixer 128 on a 32-bit ARM-V7 Cortex-A processor, and these are the benchmarking results. For implementing NHT, we require 16 vector instructions for the 256-bit input, and for multimixer 128, we only require 11. And these are the benchmarking results for different input lengths. And thank you for your attention.
Thank you very much. So we have some time for questions. Or maybe I have one. So if we look at the table here about the performance, for the speed goes down and then goes up.
Yes.
Can you explain?
Because for SIMD in these I did not do the implementation, so I am not the best person to answer. But what I understood, because I also had this question, is that 4096, that's the sector size of these architects in this architecture. So 4096 is like the perfect. How should I say it? Like these hash functions compress inputs of this size perfectly for some reason, and beyond this, the result deteriorates for both NH and multimixer.
So, other questions? Maybe I have one more short question. So, in this instantiation, the output length is, as far as I understand, for multi-mixer 128, it's 512 bits.
Yes.
Is it the same as NH?
Yeah, NH has 256.
Wait, okay. Okay, so the output different output lengths are also different.
Yes.
Okay. Okay, so let's thank the speaker again. Thank you very much. Okay, so the last talk of this session is about a small stretch problem of the DCT scheme and how to fix it. The work by Yu Chao Chen, Ting Ting Guo, Lei Hu, Lina Shan, Shupi Mao, Pen Wan, and Yu Shao will give us that talk, please.
Thanks for the introduction and the opportunity to present our work. This work proposes a systematic technique to linearize the BRW polynomial employed by the DCT scheme. And second, we show that although DCT employs the BRW polynomial, it still suffers from a small stretch problem similar to that of GCM. And finally, we propose a variant of DCT named robust DCT or RDCT with minimal modification, and we prove its security. DCT was proposed by Follow et al. In ACISP 2017. It's a beyond birthday bound DAE scheme, ensuring integrity by adding redundancy, which can be shown by the left figure, the encoder operation. And the instantiation of DCT employs a CTR-like encryption scheme, a permutation E, and the BRW-based UHF H. The encoder operation encodes the top bits of the 0 into the messages. Top bits of the 0 into the messages. So since the GCM uses the J-hash and DCT uses the BRW-based UHF, both of them are polynomial-based universal hash function. In 2005, Ferguson's proposed a further attack to the GCM. The core of this attack is to linearize the J-hash. So a natural and straightforward idea is can we apply the Ferguson's method to analyze DCT scheme? And the answer is yes. When the stretch length tau of DCT is small, we can choose a special unblock messages and reduce to the number of queries required by successful forgery to this bound. And our attack can efficiently balance the space and time complexity. Let's look at the effects of the Ferguson's linear modification technique. The authentication function of GCM can be denoted as T. The latter part of the T is actually J-hash. So when GCM uses a 32-bit tag, and the adversary knows the ciphertext for a message, the Ferguson's method can cut the complexity of queries to this bound. Can cut the complexity of queries in half. It's amazing method. Now let's look at the universal hash function of DCT. It can be denoted as the connection of two independent KBRW polynomial function. And the KBRW polynomial function is defined in definition 1. It's just the P times the BRW polynomial. And we can find it's defined recursively when the message length is less or equal or less than 3, a specific expression is given. And there is also another parameter t, which is a partition of the message blocks. For the latter part of the messages, we use this to calculate, and for another is this. So it's a forgery attack. After we modification the CR, the forgery is successful if and only if after we modification CR, the forgery success is successful if and only if the most significant top bits of the ML is all zeros. So this attack is reduced to the problem of looking for modification or difference. D is CR XOR CR prime. While keeping this equation is established. Now let's look at how to linearize the KPLW polynomial function with special length messages. When the message length is 3, we get 3 input message blocks M1 to M3. And we leave the value of M1 unchanged, which means D1 is 0 and only modify D2 and D3 by unknowns, and only modify M2 and M3 by D2 and D3 respectively, so that the KPLW function is a linear function of K about the addition and multiplication operations. So next we consider the case when M is 7. We get 7 input message blocks M1 to M7. In order to let the M4 be a variable and can be modified by D4, we must let the value of M1 be 0. And we let the M235 remain variable, which means D235 is others, and only modify the M467 by unknowns D467 respectively. After that, we will get a linear function of K. So in order to linearize the KPLW polynomial, we divide the input message blocks into 6 disjoint sets. According to the subscript of the messages. And we found that which specifies how the message blocks should be valued. First, the set V0 and V1 are set of blocks that can be chosen arbitrarily and modified by unknowns D1, D2, or DI. For example, when U is 2, the input message, the length of the messages is 3. So we can let the V0 be the set of M2 and M3, which means they can be modified by D2 and D3. And the second, A0 and A1 are set of blocks that can be chosen arbitrarily, but cannot be modified by DI. For example, in this case, the value of M1 should remain variable. Once the value of M1 is determined, we cannot change it, or DI is 0. Third, F0 and F1 are sets of blocks that must be fixed as 0 and 1 respectively, and cannot be modified by DS. For example, M1 should be 0. Next, we have already analyzed the KPLW function when U is 2 in the previous slide. And next we consider the KPLW M1 to M7. We consider this term, and we found the V30 originate from the subset +4 of elements in V20, which can be shown by the colored arrows. For another example, V40 originate from the subset +8 of elements in V30. And we also found that M4 can be modified by D4. It's a new variable. So we get this, and we can. So we can find we finally found we can determine each how these message blocks should be valued according to the subscript of the messages. We can recursively determine the 6 set. So we formalize the above deduction as the following theorem 2. We get 6 recursions according which specifies how the message blocks should be valued. After that, we will get a linearized KPLW function. But sometimes usually may select arbitrary length messages to query the scheme. So we analyze how to linearize the KPLW with generalized messages. And we will get a similar conclusion, and we will not repeat her. So the general steps of our attack is as follows. First, we select a particular message M to query the scheme. And next, we consider the stretch separately. For the latter part of the stretch, we use the method according to the theorem 2. And after that, we will get a linearized KPLW function, and we will calculate a set of solutions D or satisfying the most significant U bits of the stretch will be all zeros. For the latter part of the stretch, we will repeat about 2 to the tau minus U decryption queries until we will get a successful forgery. Our attack works due to the way because of the way DCT deals with the stretch. DCT encrypts the ML by XORing the output of the UHF. So we added a new line, the red line. We slightly modify the DCT scheme and to avoid this problem. The new scheme is called the robust DCT, and or RDCT. Encryption or decryption of DCT will lead to a random output. This modification forms a tweakable block cipher, IDE based on H and EK3. This idea is similar to the paper which proposes the GCM RUP scheme. And the core of RDCT is an instantiation of UIV construction. Next, we is lemma 5 Lemma 1 and Lemma 2 proposed the confidentiality and the integrity advantages of RDCT. And we also can get the DAE advantages of RDCT. We can find the third term of this bound is not affected by the message length, but the probable bounds of DCT is actually affected by the message length M. When we make the Q decryption queries of M blocks, this bound will greater than 1. So the security of RDCT is better than the DCT scheme. Next is a comparison among these schemes. We can find in order to attack the RDCT, we need about 2 to the 10th power of decryption queries. So our modification is effective. Summary, we show that although DCT employs the BLW polynomial, it still suffers from a small stretch problem similar to that of TCM. Second, we propose a variant of DCT named robust DCT, which has a better security bound. Thanks.
Thank you very much. So we have some time for questions.
Hi, Chen. You focus on DCT. You focus on the attacks on DCT in your work, right?
Yeah.
I wonder if your technical properties in this paper could be applied to any other BRW-based AE schemes.
Theoretically, yes, but other BRW-based encryption scheme or authentication scheme uses a full stretch, not a small stretch. So the complexity of this attack is actually impractical for this BRW-based scheme.
Oh, so you focus on DCT, right? Because DCT use a shorter thread, so you focus on it.
Yes.
Oh, thank you.
Other questions? So maybe I have one question. So you, in the robust scheme, you added one line to the output of the block cipher?
Yes.
And maybe can you explain why this solves the issue of the length independence? If you have some high-level idea why this solves the issue?
This construction is actually can input arbitrary length tweaks and XORs the input and output of the EK3. So this construction, the output of this construction is actually random. So after modification CR, it will lead to a random ML or to stretch.
Okay. Okay, thank you. Any other questions? If not, let's thank the speaker again. Thank you. So I think we have coffee break until 3:30.